Welcome students to today's lecture on general aspects of experimental nuclear astrophysics. So, up to now in the course you have seen different burning stages, different processes after the iron peaks, nucleosynthesis of elements beyond iron peak and salient features of the universe and resonant reactions, non-resonant reactions. So, all these mostly physics point of view the topics were covered, and by now it is very clear that the chemical elements in the universe and the energy produced from the stars and different entities in the universe, they are because of nuclear reactions, right. It stems from the nuclear reactions. What are the fingerprints of these nuclear reactions? It is the abundance curve and many other features also we have seen. So, one of the most important fingerprints in the universe for the nuclear reactions is the abundance curve. But it is not sufficient to understand the speculations or the qualitative discussions. It is also important to understand the quantitative aspects of the abundance curve. So, how do we understand the quantitative aspects of the abundance curve? We have to measure the nuclear reaction cross sections. We have to measure the nuclear reaction cross sections. So, you have to carry out nuclear reactions using different facilities available. Depending on your requirement, available resources, the reactions have to be carried out, right. So, in the last lecture we have seen S process, R process, which are basically neutron induced capture reactions, radiative capture reactions induced by neutrons, where gammas are emitted. So, to understand the cross section behavior of this neutron induced capture reactions, you have to measure the gamma rays and what are the experimental aspects involved. Those things we will discuss in today's and upcoming lectures. So, what was the summary of the previous class? We have seen the synthesis of elements beyond the iron peak because of the S process and R process, and very few elements, 35 nucleides, which are termed as excluded isotopes by Cameron, that is P nuclei, whose abundance is very low. So, this was the summary of the previous class, and in today's lecture let me give you some information about the components that we normally use as part of experiments relevant for the nuclear astrophysics. What are the components we have to have anyway, okay? And then what are the sources of the charged particles which are inducing the reactions for the synthesis of elements before the iron peak? What are the sources of those charged particles? And then what are the sources of neutrons which have mass but no charge? What are the sources of these neutrons? How to get this source of neutrons, and how experimental measurements have to be carried out? What are the precautions? What are the salient features? These things we have to understand. So, in this course I will not go into the deep of these aspects, but I will try to give you some kind of framework, all right. So, what are the general experimental aspects of nuclear astrophysics? So, we can divide the nuclear reactions relevant for nuclear astrophysics as two types of measurements. Number one, direct measurement. Number two, indirect measurement. What do you mean by direct measurement? If you have the resources to carry out the reactions the way they are happening inside the stars, in terms of flux, the number density of the nucleides involved in the reaction and the energies, if you have the enough resources available, then if we carry out those kind of measurements, then we call them as direct measurements. But there are challenges in carrying out the direct measurements. There are two important challenges in carrying out the direct measurements. What are those? Number one, extremely low cross section. We have seen the reactions do happen below the Coulomb barrier, most of the reactions in the stars, and in order to measure the nuclear reactions using facilities available on Earth, the cross sections which are very less, very low cross sections have to be measured, and measurement of low cross section always invites problems from the uncertainty. Either with the available energies, you have to measure the cross sections and then you have to extrapolate. Then the extrapolations always invites the uncertainties. So, this is one challenge. And another challenge is, many a times the nuclear reactions happening within the stars, they involve the unstable nuclides. It is not possible many a times, and it is almost impossible to prepare a target of unstable nuclides and do the nuclear reaction measurements. So, it is because of this, one of these reasons where people go for the indirect measurements like charge exchange, particle transfer, scattering. So, this kind of indirect measurements people prefer for carrying out the nuclear reactions relevant for astrophysics. And for photo disintegrations, we need to use the gamma rays, but very rarely the gamma sources are available on Earth. So, you have to go for the indirect measurements, okay, if the reactions are induced by gamma rays. And light particles like protons, electrons, whatever reactions they induce in the stars, they also have to be measured using the available resources. And it is the accelerator for charged particles and also for neutrons indirectly. Okay. So, accelerators have to be used to produce the beam of the particles to carry out the nuclear reactions, and you have to have targets which should be stable throughout the nuclear reactions, and the thickness determination also plays very important role. More features about all these components I will discuss one after the other. Okay. So, number 1 accelerators, number 2 targets, then nuclear reaction will happen when the particle beam from the accelerator reacts with the nuclei in the target material, all right. And because of the nuclear reactions, whatever particles are emitted, mostly gamma rays, you need to use detectors of high efficiency and also of very good resolution if you want to detect gamma rays whose energies are closely separated from each other. Then you need to have pulse processing systems, either you can go for analog system or advanced digital data acquisition systems. So, for analyzing the pulses from the detectors, you need to have pulse processing systems, and then you record the spectra or the pulses, and then you analyze using some software. Fine. In general, when nuclear reaction is happening, lot of unwanted radiation comes out because of the nuclear reactions, and the surroundings have to be shielded from the experimental setup. So, you should have appropriate and sufficient number of shielding materials surrounding the experimental setup. Otherwise, not only it can harm the surrounding personnel, though they will be much away from the experimental setup, but many a times it will hamper the quality of the data obtained from the nuclear reactions. What exactly we measure from all these nuclear reactions which are relevant for the astrophysics? Of course, the fundamental quantity is reaction cross section, and many a times we wanted to measure the excitation energy. How do you measure the excitation energy of the nucleus after the reaction is formed? And if it is having some resonance, then what are the energy levels which are giving rise to the resonance? So, you have to measure the resonances also, and then for each energy level of the compound nucleus, what are the spins and parities? And during the de-excitation from the excited state, if more than one gamma rays or more than one particle is emitted during the de-excitation, many a times researchers, they look forward to understand the angular correlation between the particles emitted during the nuclear reactions. So, we need to understand the angular correlation. So, you have to use different detectors at the same time. That will help us in understanding the angular correlation. Hope you are aware, in the teaching laboratory, you might have seen a source called as cobalt-60, which emits gamma rays in cascade. The angle between these two gamma rays emitted from the cobalt-60, it varies within a range. And if you take sodium-22, gamma source, it emits 511 kV gamma rays in opposite directions. There also you can study the angular correlation, and you will see that maximum number of counts you will get when the angle is 180 degrees between the two gamma rays. And we also might we also might want to measure the lifetimes of these nuclear levels and the branching ratios, that is transition probabilities of the energy levels. So, all these parameters we want to measure in order to understand the nucleosynthesis happening within the stars and in the universe. So, as I said, what are the important components which are useful to carry out nuclear reactions? Particle accelerator, good quality nuclear radiation detectors. When I say good quality, I will give more details in upcoming lectures. And then target materials, which should be very stable when beam interacts with the target, and pulse processing systems and the shielding materials. So, these are the important components of any nuclear reactions relevant for astrophysics. Of course, if you do not have any facility, just go for theoretical aspect, but we need to have an idea about the experimental aspect of the nuclear astrophysics as well. All right. Let us start with the charged particle beams. What are the general considerations for the charged particle beams? The general considerations, they look like this. Collimation. The particle beam coming from the particle accelerator, it has to be collimated well. Otherwise, instead of falling on the target material, it can fall on the material surrounding the target material, and it can give you unwanted radiation. So, the collimation plays very important role, which can be achieved by using magnetic slits and using various methods within the accelerator. So, the collimation is one of the important properties, important consideration which has to be taken into account. So, you have to ensure that beam is exactly falling on the target material, and then the spot size has to be decided so that it covers the target material. So, of course, the spot size diameter should be less than the size of the area of the target material, front surface of the target material, and the better spot size and the better quality of the nuclear reactions. And this is where beam optics comes into picture. And then beam current. Can you assume the current should be less or more to carry out the nuclear reaction relevant for the astrophysics? Remember, we are dealing with nuclear reactions having very low cross section. So, for accurate measurement of the cross section, of course, you need large number of incident particles, because already cross section is very low, and if the beam current is also low, then the ejected particles will be less and the statistical fluctuation will be more, and it will lead to the uncertainty in the measurements. So, more current is in general preferred for the measurement of nuclear reactions. And in what steps you have to use the energy steps, and in what steps you have to change the energy. See, if you are interested in finding out the resonances separated by, which are closely separated from each other, then the energy step should be very small. Fine. So, in this normally we go for 100 electron volts, or sometimes depending on the energy level diagram, we can increase the energy steps. But small value of energy step better is for getting the information related to the resonance phenomenon. And then the spread of the incident particle beam should be less, and we normally prefer it should be in the order of electron volts, because more spread and leads to the more spread in the cross section values. Because when we want to have nuclear reaction at a particular energy which is happening in the stars, though there is a small spread around the centroid of the gamma peak, more than that, if there is a spread in the incident particle beam, then of course, whatever data you are acquiring, that is of very bad quality. And not only beam, the target also should be free of the contaminants, and the absolute energy calibration of the particle accelerator is very important. So, what are the methods of this energy calibration? What are the reactions which are useful? That we will discuss. All right. And in accelerator, if you see what kind of accelerators we come across. So, you are aware of Van de Graaff generator for relatively less energy of the proton beams, okay. And then one can go for the initial version of the linear accelerator, that is Cockcroft-Walton accelerator, and one can go for dynamitron, one can go for tandem accelerator, and for compact size one can go for the cyclotron, and we can also use synchrotron, which is the extended version of the cyclotron. So, the details of these accelerators are available in many textbooks. So, you are suggested to go to those textbooks and read them, so that you can understand the basic principle of all these accelerators. So, in the linear accelerator, of course, the basic principle is acceleration of the particle in the presence of electric field, and in the case of cyclotron, magnetic field is used to allow the electrons to follow the spiral path, and also electric field for the accelerations. And if magnetic field is changing with respect to time, then we call it as synchrotron. So, I am not going to discuss the details of these accelerators, their working principles in this lecture. Just I am giving you names of a few particle accelerators which are relevant for nuclear astrophysics, all right, and also linear accelerator, which produces more energy for the charged particles, which uses the different steps of accelerators in the LINAC. So, in India we have one LINAC in TIFR, and people are successfully doing the experiments using this LINAC facility. So, when this LINAC facility is important? Direct or indirect measurement. See, as I said, LINAC is producing high energy particles, but that much high energy is not involved in the stars. So, direct measurements are not possible to understand using LINAC. So, for indirect measurements, yes, LINAC is highly preferred, all right. Now, these are the some reactions, laboratories, energies and widths of the narrow resonances, which we use for the ion beam calibrations. For example, proton on oxygen 18, when it gives alpha particles, the width of the resonance is, you see, it is electron volt, 130 electron volts, and the lab energy is 150. So, these are the energies involved within the stars. So, direct measurement, all right. And for fluorine 19, sodium 23, magnesium 24, aluminum 27, which is a widely used reaction, because you have different energies. Even one reaction is sufficient to for the energy, ion beam calibration. This one reaction of proton aluminum 27 is sufficient, because aluminum 27 is widely available, and you see the widths in electron volt. So, for the calibration of ion beams, we have to carry out this kind of reactions first, and then you go for the reaction of your interest to study the nuclear astrophysics. So, this table shows a compilation of laboratory energies, not center of mass energies, but laboratory energies and widths of the narrow resonances. Now, coming to this neutron beams, earlier I have discussed about the charged particle beams. Now, I am discussing the neutron beams. LINAC is widely used for the production of neutrons. So, in these beautiful experiments, let me explain how it works, how neutrons are produced. See, this pulsed high energy electron beam, okay, is used to produce neutrons whose energies are from a fraction of keV to several hundred keV, of course, after moderation. Okay. And then this LINAC pulsed high power electron beams whose energy is 50 MeV, when we allow it to fall on this target, okay, this is a target material, then neutrons are produced via spallation reaction, So, let me give you some information about this spallation reaction. What is the spallation reaction? It is a violent reaction in which a target is bombarded by very high energy particle, in this case electrons, and the incident particle, it denigrates the nucleus through inelastic nuclear collisions, and it involves the breaking up of the target nuclei into several constituents, and the result is emission of protons, neutrons, alpha particles and other particles. And the neutrons produced in this kind of reactions, they can be extracted and used in experiments. So, whatever neutrons are produced in these reactions, we are going to use it for further using another target material, fine. And here this is the spallation target in this case, and which emits spallation fragments. In addition to that, some other particles also produce like neutrons, and the number of neutrons produced here depend on the type of target material and also the energy of the incident particles, all right. And in general, not in this case, in general the target material in the spallation sources are high Z materials like lead, tungsten and silver and bismuth. Now, when I say fragments are emitted in the spallation reaction, you can immediately recollect the fission process. In fission also, when thermal neutron reacts with uranium-235 and uranium-236 is formed, there also fragments are produced, there also neutrons are produced. And in spallation reaction also, fragments are produced because a decay of the compound nucleus into fragments is happening. In addition to that, neutrons are also emitted. So, what is the difference between spallation and fission reaction? The basic difference is, in the fission, whatever neutrons are produced, they can initiate further fission, and that is a basic principle of nuclear reactor, right, that you are aware of. It is a chain reaction, but whereas in spallation reaction, the neutrons produced in the primary reaction, that is a incident charged particle with the target material, when they produce neutrons, these neutrons cannot initiate another spallation reaction. Hope it is clear to you, right. In fission process, in the primary reaction, whatever neutrons are emitted, they will initiate another fission reaction, whereas in spallation, when neutrons are emitted in the primary spallation reaction, those neutrons cannot initiate another spallation reaction, fine. So, in this particular case, if you see, it is basically lithium kind of target is used sometimes, fine. So, though it is not exactly spallation reaction, neutrons when they react with the lithium sample, they also emit the gamma rays if you want to study that kind of reaction. So, spallation kind of reaction can be assumed when proton reacts with lithium, because it is also source of neutrons. As I said, one of the important topics in today's lecture is what are the sources of neutrons. So, one can produce the neutrons by allowing the charged particles with heavy metal target, or one can produce the neutrons by allowing the protons or electrons on a target material. So, another example is proton plus lithium 7, which gives rise to beryllium 7 and a neutron, and proton plus beryllium 9, which can give rise to beryllium 9 and a neutron. Okay. So, let us continue this one, and after neutrons are produced here, see high level of shielding is arranged here. And what kind of shielding material is used? For the neutrons, either use a very good quality concrete, normally we use the concrete material for the shielding of neutrons, and you collimate it. As I said, one of the important consideration is collimation. You see, from this target, when electrons react and via gamma n reaction, neutrons are produced, they are collimated in this way. See the laser pointer, okay? And when these neutrons interact with the target material, which is inducing capture reaction, that is why I am using n gamma sample. These gamma rays have to be detected by using detectors. Maybe it could be semiconductor detector like high purity germanium, or scintillation detector like lanthanum bromide or sodium iodide detector, and depending on the application you use one or more than one detector. And neutron detector also can be placed here, because to monitor the neutrons which are coming from this primary target material, all right. And because of the very intense background due to Bremsstrahlung, this is a process which is a very important considerations in these nuclear reactions. Bremsstrahlung. So, heavy shielding of targets is required. What is Bremsstrahlung? It is one of the processes by which, not only in this kind of nuclear reactions, but in the nature also, Cosmic rays from the space, they dissipate some of their energy in the Earth's atmosphere, and solar X-rays have been attributed to bremsstrahlung generated by fast electrons passing through the matter in the part of the Sun's atmosphere, which we call as chromosphere. And not only in the atmosphere, but internal bremsstrahlung also arises in the radioactive disintegration of the beta decay, which consists of production and emission of electrons by unstable nuclei. Okay? And these electrons deflected in the vicinity of their own associated nuclei, they emit internal bremsstrahlung. So, within the high electric field of the nucleus, the electrons undergoes bremsstrahlung process. And as I said, using Linac accelerator, high energy proton beams can be produced via spallation reactions. Okay? And this is another reaction to reduce the shielding material, use Van de Graaff generator, and though neutron flux is less by 3 to 4 orders of magnitude, we can also reduce the burden on the shielding material. The plus point is that there is no bremsstrahlung, okay, and less load on shielding, and flight path is also less. In the previous diagram, if you see, here the flight path is 50 meters. So, here we are using time of flight technique, which I will discuss in detail in upcoming lectures. So, this time of flight technique is normally preferred considering the light path taken by the gamma ray, which travels with the speed of light, and neutron velocity, of course, it travels with velocity less than the speed of light. So, that is how this flight path is defined. Okay? And depending on the energy, one can have a control over the angle with which neutrons are emitted. All right? And lithium detectors for producing and also for monitoring the neutrons. For producing the neutrons, lithium 7, as I said, protons plus lithium 7 gives rise to beryllium, okay, and it gives you neutrons, isn't it? And if you allow proton to fall on the beryllium 8, then it is beryllium 9, boron 9, and neutron is produced. So, here I am also using neutron flux monitor, so that I come to know what amount of neutrons is emitted in the reaction. And we always prefer to have the precise energy distribution of the thermal neutrons after the moderation, right? And this is about 25 keV in this beautiful experiment, and the direct measurement of the Maxwell-Boltzmann average cross sections, and we prefer, instead of time of flight technique, here I go for activation technique, whose details I will discuss in upcoming lectures. All right. So, with this I will close today's lecture. So, to quickly summarize today's lecture, what I have discussed: important components which are required to carry out nuclear reactions relevant for the nuclear astrophysics, and some considerations for the particle beams, how to produce the charged particles using different accelerators, and how to produce the neutrons, and only after thermalizing them we can carry out the nuclear reactions. Otherwise, those neutrons energies are very high, whereas in the stars energies are very less. So, using the moderators of sufficient thickness is also very important, and many more aspects of detectors, targets I will discuss in upcoming lectures. Thank you so much for your attention.